Good evening, everyone. So, welcome to another webinar organized by SLTC as a part of the national webinar series entitled Climate Smart Sri Lanka. So, the series is organized by SLTC as a responsible higher education institute under the guidance of the Vice Chancellor, Professor Chandrika Vijayaratne. And also, we are honored to have the IEPSL, which is the Institute of Environmental Professionals Sri Lanka, as the joint strategic partner in this initiative. So today's session focuses on fire and safety of structures during disaster. And this is conducted by Dr. Pasindu Veerasinghe from the Department of Civil Engineering at University of Moratuwa and Professor Chaminda Bandara from the Department of Civil Engineering at University of Peradeniya. And the session will be moderated by Dr. Sumudhu Herath from the Department of Engineering at University of Moratuwa. So prior to starting a session, I would like to request all of you to engage actively in this webinar, and we will be opening up the Q&A forum and the chat section open throughout the webinar, where you will be able to send your questions and the moderator will be asking those questions during the Q&A round from each speaker. So with that, without further ado, we would now move on with the webinar. And to guide this important discussion today, as I mentioned earlier, we are honored to have Dr. Sumudhu Herath serving as the moderator of the session. So let me formally hand over the session to him after his esteemed profile. Dr. Sumudhu Herath is a civil engineer and an academic specializing in steel structures, structural optimization, computational modeling, and machine learning applications in the structural engineering domain. He is currently a senior lecturer in civil engineering at the University of Moratuwa, Sri Lanka, where he contributes extensively to teaching and research across undergraduate and postgraduate programs. Dr. Herath earned his PhD in civil engineering from the University of Cambridge, United Kingdom, supported by the prestigious Cambridge Trust Scholarship. His doctoral research focused on multi-scale modeling of woven and knitted fabric membranes, combining computational mechanics with advanced statistical and machine learning techniques. He completed his BSc in civil engineering with first-class honors from the University of Moratuwa, graduating with a record-breaking GPA and receiving multiple gold medals for academic and all-round excellence. His early education was at Royal College Colombo, where he ranked second nationally at the GCE Advanced Level examination. Dr. Herath is an active researcher with over 20 Q1 journal publications and more than 50 technical publications to his name, reflecting his sustained contributions to high-impact research in structural and computational engineering. His research interests span computational mechanics, multi-scale material modeling, finite element modeling, and machine learning applications in structural engineering. Dr. Herath has served as a visiting professor and research collaborator at the Indian Institute of Technology, Delhi, the Technical University Darmstadt in Germany, and has also worked as a research assistant at the Swiss Federal Laboratories in Zurich, Switzerland. So with that, I would like to gracefully invite Dr. Sumudhu Herath to accommodate the session today. Dr. Sumudhu, over to you.
Right. Thank you, Mayangana. I hope I'm audible.
Yes, you're clear,
yeah,
sir.
Right. Thank you. And good evening to everyone who is present, and a warm welcome to this session of the Climate Smart Sri Lanka, Awareness to Action, Threats, Vulnerabilities, Lessons Learned, and Future Preparedness Knowledge Series. To give you a small opening remarks before we move on to the lectures, Sri Lanka today stands at a critical juncture where climate-induced disasters are no longer rare or isolated events. Floods, landslides, heat waves, industrial accidents, or post-disaster fires are increasingly intersecting with our built environment. So as engineers, or planners, policymakers, academics, and practitioners, we carry a shared responsibility to ensure that our structures are not only designed to withstand normal conditions, but also to perform safely under extreme and more often unpredictable disaster scenarios. So the focus of today's session, fire and safety of structures during disaster, is therefore both timely and essential, and also very important. And fire hazards during disasters, whether triggered by earthquakes, floods, industrial failures, or human actions, pose severe risks to life, infrastructure, and recovery efforts. And understanding these risks, learning from the past failures, and embedding safety and resilience into structural design and emergency planning are key components of climate smart developments. And we are privileged today to have two highly respected resource persons who bring both depth and diversity of expertise to this discussion. First, Professor Chaminda Bandara, who has made significant contributions to the various fields of structural engineering, including structural health monitoring, disaster resilient designs. And also Dr. Pasindu Veerasinghe brings strong insights into fire safety and the related structural performance of structures. And their combined perspectives will help us bridge theory, practice, and also policy. And I'm Dr. Sumudhu Herath, and it's my pleasure to serve as the moderator for this session. And I encourage all the participants to actively engage via the chat, given access to all of you, and then reflect on Sri Lanka's unique vulnerabilities and gain insights from this discussion. And with that, let us begin today's session and move one step closer towards safer, more resilient and climate smart Sri Lanka. So now I will introduce the first speaker for the day. Professor Chaminda S. Bandara is a professor in civil engineering attached to the Department of Civil Engineering, Faculty of Engineering, University of Peradeniya. He has been in the engineering industry at various capacities since 2000. He is a chartered civil engineer, a corporate member of the Institute of Engineers Sri Lanka, an accredited professional of the Green Building Council of Sri Lanka, and the country secretary of the International Association for Bridge Maintenance and Safety. He is a recipient of the Presidential Awards and several other national and international awards for his research and publications. So to date, he has authored 2 books and published more than 30 papers in well-reputed journals and more than 50 papers in national and international conferences. He serves on the review panels of several international journals and on editorial committees of international conferences. His research areas include analysis of steel, concrete, and masonry structures, damage assessment of structures, structural health monitoring, blast effects on structures, disaster resilience of structures, green buildings, and sustainability aspects of structures. Professor Chaminda Bandara, the stage is yours. I hope, you are online, right?
Yeah, thank you
Stage
very
is
much.
yours, Professor Bandara. Over to you, sir.
Yeah, thank you, Dr. Herath, for that introduction. And also, before starting, I think I also would like to thank the SLTC, the Vice Chancellor, and the organizing committee. First, of course, for organizing such an important series of sessions on the in this particular subject on climate smart Sri Lanka, and also for inviting me to deliver a speech today. So I will share my presentation. As mentioned by our moderator, Dr. Herath, myself and Dr. Pasindu Veerasinghe will deliver this session today, covering starting from general aspects and then to the fire and structural safety. So the area that I will cover is here. So I will mainly focus on climate smart designs and constructions, starting from the natural, anthropogenic, and socio-natural disasters. Then as civil engineers, of course, as engineers, the contribution of the construction and building sector to the climate change, which is the main problem that we have to address. And then the global agenda, the futuristic designs, and the relevant rules and regulations that may be to be changed, to go with this new agenda. And also I will just give an introduction on design approaches and recent developments on this fire and structural safety. And then we'll hand over to Dr. Pasindu Veerasinghe. So to start, the natural disasters, of course, we know the definitions. So we have these geological, meteorological, hydrological, and biological natural disasters. And on the other hand, we have the anthropogenic disasters, that is mainly because of the action of human. And then we have this complex integration between the natural and anthropogenic disasters. We call the socio-natural side of the disasters. Of course, one of the main issues in this socio-natural complex interaction is the climate change because of the global warming. So if we look at some of these disaster records, what we see is an increasing trend of disasters, but fortunately, the reducing trend of number of deaths, because that is not because the disasters are not significant, because the countries, the world is developing. So we have a lot of technology. So to save people, the deaths, to reduce the deaths due to disasters. So therefore, we see even there is a increasing trend of disasters, the number of deaths recorded is reducing. So that is very much fortunate. And also due to the development of technology. And when looking at the significance, mainly the impact of the disasters. So what we see is, I mean, when we categorize, for example, the droughts, the flood, the storm, extreme temperature, so these are playing at a very high significance, including earthquakes. Of course, the earthquakes are kind of not mainly because of anthropogenic actions, but the others, the droughts, floods, and storms, extreme temperatures, all those things are related to the climate change. So that is why I think even this particular series of sessions have been organized by SLTC, which is a very good initiative. And a little bit about these anthropogenic actions related disasters. I think we know the trend started from the Industrial Revolution, somewhere around 1800s, and then the consumption of materials, the consumption of energy, all those things increased rapidly, as we can see in most of this literature. And at the same time, when you have high energy consumption, in return, we are emitting a lot of greenhouse gases. So again, as we see from 1800s, this increasing trend of emitting greenhouse gases. And then we know that because of all these greenhouse gases that deposits at the upper layers of the atmosphere, that blocks the heat that penetrates into the earth, trapped within. So we talk about the global warming. And according to IPCC reports, we have almost exceeded the 1.5 degree temperature rise, effect, which is kind of a very significant and very, I mean, that leads to a lot of problems in the world. So this is where we are at the moment. And so with those, we are talking about these increased natural disasters. So as a result of the CO2 emissions, the climate change, and then increased natural disasters. And so one of those is Ditwa that we experienced in November. I think when we look at all around the country, now this particular disaster, kind of the impact was for everyone, not for one region or one province. And now where I am in the central province, in and around Kandy, was one of the devastated regions. So I saw a lot of damages by myself because I am living here, and it was really impossible to think, just at that day and after 3 days until the things are cleaned out. And so now what is the relationship between this GHG emission and the construction and building sector? So that, because we are engineers, so we are responsible for a large part of this matter. Now, if you look at the records, again, the literature, you see the electricity and heat, transport, manufacturing and construction, and then buildings. There are many items that are directly related to engineering that has a very high contribution to the greenhouse gas emissions, therefore to the global warming and the climate change. So that is why I think as engineers, we should get together and discuss this. Of course, it requires all the other professionals, all the other disciplines to join hand to somehow minimize this problem. The construction sector contribution is about 40%, from building operations about 28%, and then building materials and construction about 11%. Of course, this is 2019 reports, but it can't be large or big difference even now. So that is our contribution as engineers in the carbon dioxide emission. So when we look at the population growth and also the building sector, the expected development in the future. So by 2023, we reached our population reached 8 billion, and by 2050, it will be predicted it will be 9.7 billion. So that means within the coming 25 years, around 25 years, we are expecting another 1.7 billion people to come to this, come on Earth and, be here. So what it means? It means we have to expand the available or existing cities. We have to build further, the infrastructure, because this 1.7 billion within the coming 25 years will join us. So they need infrastructure as we need now. So that means we are talking about further, consumption of material, consumption, emission of carbon dioxide, if we don't take serious action. Now this is Colombo. The urbanization from 1988 to 2022. I think we can understand how much the environment has changed in this, several decades in our capital city. So that is how the development is going on. That is how the urbanization is happening. The cities are expanding. So the issue here, when we compare this city expansion with the greenhouse gas emission and also this climate change problem, is now to convert the carbon dioxide or the greenhouse gases back to, the oxygen and the other non-greenhouse gases, the main thing that we need is the greeneries. So what we do is, when we expand cities, the existing greeneries are reducing, isn't it? So then how we can convert this carbon dioxide back to oxygen if we expand our cities in this way? Actually, that is why in the smart development, we are not talking about expanding cities, but we are talking about vertical expansion, not the horizontal expansion that we will discuss in the coming slides. And also, as I said, now presently, the building sector GHG emission is about 40%. And by 2050, with this expanding cities for this 1.7 billion people, right, who are coming into the world, so this will increase to almost 50%. So that is where the future problem is. So that means we need to take action now as engineers to have a very systematic, very controlled engineering for a smart development. So as I mentioned, the material usage is rapidly increasing. And when we look at the construction raw materials, so the urban construction raw material utilization in 2010, it was around 40 billion tons a year. In 2025, it was about 65 billion tons a year. And by 2050, it will be 90 billion tons a year. So therefore, we are already we are in a material scarcity, right, that we know. And the requirement we are expecting is kind of far exceeded what the planet can produce. So that is the other issue that we have to think about. Because, so as I said, we have to expand cities. We need to provide infrastructure for the people, because everybody should have equal opportunities for living. But this is the problem that we have in the construction sector. So here we talk about the future designs, the smart designs, the green buildings, the green cities, and all those. So the climate resilient infrastructure is coming here. So if we have, the climate resilient infrastructure is, that means we have to look at the disastrous side, because already the climate change is happening. So the disasters are aggravating. So when we, as engineers, when we design infrastructure, construct them, so one of the main things to look at is the disaster management aspects. And then to conceive the existing natural resources, because as I said, there is a material scarcity. So we talk about, and again, the recycling and reuse of existing materials as much as possible in our construction. And then, of course, the reduction of the CO2 emissions, use of renewable energy, and all the energy efficiency related areas. So this is, I think, where we should be heading. And also the global agenda is towards this direction. So when we come to these sustainable designs and construction, so as I said, so these are some of those definitions. And we have to look at the resilience. We have to look at the sustainability. And accordingly, we are talking about energy independence, water independence, renewable resources, to mitigate the resource shortages and environmental effects, and the combination of all the experts, the community support in this process. So we have the global agenda, the Sustainable Development Goals. And as we know, two goals, the goal 9, which is focusing on the resilient infrastructure, and then goal 11, once again, focusing on the same side. So there are already defined targets that even as a country, we have agreed to follow these, so kind of achieve these targets. So that we have to remember. And also the Sendai framework, where we talk about the to go with the framework to minimize the disasters and the disaster effect on the communities. So then about the futuristic designs. So one important thing is, now it's not always, we try to develop all the places on the earth or in this planet. So we have to, because we have to identify where to develop and what cost we will have in those developments, because then it's a optimization problem, because hazards are there. That now these are some of the things we have seen, right, in this recent disaster. So hazards are there. If you are not there, you are not exposed to it. If there is exposure, then we have a risk and also the vulnerability, and then these disasters can happen. So with deaths and damage. So this should be very well considered when we do our designs. Whether those especially the hill country area that I am living, we have seen most of the issues, most of the deaths because of the landslides. And we know that most of those lands, there have been no assessment. So maybe the people, they don't know, whether those are risky places for them to live. So those are the issues we have. So as I said, this is a optimization problem. Now, so when we look at this optimization problem in detail, so what I'm trying to explain here is, so we have a population to serve, and there are natural disasters. Not everybody is exposed to these disasters, as I said. Those who are exposed to it is only part of the population. When the population is growing, that exposure or the number of people exposed to the disasters also is increasing, because people will go and build their infrastructure wherever possible, right? Because they need those. So with the increasing population, therefore, the exposure of people to the disasters will expand or increase. And the other thing is, if the disaster, if the natural disasters are increasing, then also the population will start affecting to it. So that is the other way. Like when there is a lot of rainfall in the upcountry, we see the damage happen in the cities, even up to Colombo, with a lot of flooding. So because when you have aggravated disasters, the population who were not in a disaster prone even zones can affect. So therefore, the requirement is to shift this, the population away from the natural disasters. So for that, we need, as I said, a smart construction, then the related public policies, awareness of people, and various knowledge improvements. Now, therefore, the key considerations in futuristic structural designs can be discussed in this particular slide. So as I said, it's a risk and vulnerability optimization problem. So we have various structural models. Simply, these are some of the examples. If it is a earthquake-prone area, the base isolation and damping systems in our structures. Maybe if it is a very highly flooding area frequently, the floating systems. And then if it is very wind vulnerable areas, then the aerodynamic designs, the prefabricated or the modular designs, and also then the use of innovative materials. Of course, there are many self-healing concrete, cross-laminated timber, so many. And then the smart technology, including digital twins. So you can real-time monitor the structures. So any of these two can be, so I think you can see several regions. So if you have smart, the structural models with innovative materials, so that's a good trend. So if we have structural models and smart technology, that's a good trend. If we have smart technology and innovative materials, that's also a good trend. But if you have all three, that is the best in our optimization problem. Now, the key considerations in this case are here. Now, the structural design codes. So as we know, we use design codes for our designs. So are these codes evolved enough for such smart designs? I am sure the codes are evolving, but still there is a lot to do. Of course, those are the engineers that who should do these things. Then these fixed rules in design codes should be flexible, and the design should be mostly performance based and not rules but frameworks. And we need to get the AI assistance in our designs, the smart materials, flexible structural forms, so they can adapt to various situations and all that. So that is one side. On the other side, the rules and regulations, the building approval, the regulations. So are we still can go with these strict rules and regulations? Even rules are there, sometimes we are not following it. That's a separate story. But to go to this, there are a lot that we have to do. And also a little bit about the planning and approving authorities. Of course, we know SIDA is one of the authorities that had the most of the legal powers, and then the local governments that give building approval, the building permits in our construction, and then the Urban Development Authority, NBRO, to once again to give the clearance for especially the slopes in the mountainous terrains, the CCD, the Coast Conservation Department, if the construction is in the shoreline, and also especially the fire brigade that we will be talking about because they are the one of the authorities that inspect the building fire related issues and also the fire plans. So should be empowered, more than now. Because why I am saying so is, I think maybe we all know, we can speak openly because these are public things. For example, we know that the resources for the NBRO to kind of clear out most of these damaged areas, especially the school buildings, was an issue during this Ditwa. So therefore, University of Peradeniya, of course, University of Moratu also came to Kandy to go and look at these school buildings to help NBRO to give clearance so the schools can be opened, because they don't have that adequate infrastructure, the resources to do that. So there is a lot in our country to do in that direction. So I have just 2 photos here from Ditwa. Now this is around Peradeniya. What you see is the Mahavali River, but this is just after the the flooding. So what you see is, even there is a regulation that from the center of the river or from the edge of the river, there is a regulation that we all knows that you can't do any construction. But this is what really is. So how we can? So that is why I am saying. So we built at vulnerable places, we exposed to the disasters, and then it's very difficult. And this is the second picture I want to show. Now this is on the Gampala-Navalapiti road at Ulapane. This is one of the massive landslides. Actually, I am daily traveling on this road. The road was closed about about 5 weeks because of this landslide. You see how many structures collapsed. Now, this was a already notified place, but still there were buildings. The cracks on the road was there for many years, about 10 years. I am traveling on this road. But there were structures built. So that's about this, the general thing that we all should look at, with respect to the basic things that we should consider as engineers in our futuristic designs. I will give a little introduction to the fire hazards. Of course, Dr. Pasindu Veerasinghe will elaborate a lot of things in this section. Now, so there are 2 things to consider. Of course, fire can happen at any time. So that is normal fire hazard of building. So we have regulations, rules, everything for a normal fire hazard. But the issue is, if there is a fire during a disaster, so then the situation is worst, will be worst, because a disaster means now we are already in a problem, and then if a fire comes, so how resilient we are. So there are all these various residential and apparel, chemical, hotel, various divisions of structures in the fire designs. There are various categories of structures, and then the reasons can be, the fire disasters can be due to structural failures in buildings, maybe due to electrical system damages, the wiring shortage, the shortages of wiring faults and all that. And then the generator-related misuse, gas leakages, spill of flammable substance. So a lot of reasons can be there. And then also the incorrect building designs, use of substandard materials, improper firefighting systems, and also the human factors. All these are reasons. And if we just look at records of fire hazards, we can see that the building fires are one of the largest. If you see now, this is again world fire statistics. Electrical equipments, the then gas and related fires, and also the smoking related fires, carelessness. So there are many factors that cause fires in buildings. And also the deaths, if you see, most of the deaths are due to residential building fires. Now this is 2020, and the second chart is 2023. So it's about 85%. the fire-related deaths are due to residential building fires. So we have to pay a lot of attention to this direction. So in the structural fire designs, of course, we know that of course, in Sri Lanka, we have almost adopted using Eurocodes. And there are, especially the design of concrete structures and the composite structures, there are several common areas looking at, whereas the design of steel structures and aluminum structures, so there is little different areas or the closest to look at. And timber structures, of course, it's kind of different a lot from the other codes, and also the masonry structures. So that is the available design tools that we usually use. And also, I think we know that for the Eurocodes, we have the national annexes, and fortunately, we have the fire design national annex also by the SLSI. So I think this is something noticeable that because we are also updating in the design codes with the local input. And design fire scenarios, when we look at, we have these three situations, the accidental design situations, especially, the accidental design situations are, I think, applicable. Accidental design can be this disaster, for example. Then the structures where a particular risk of fire arise as a consequence of other accidental actions, so relevant to disasters, for example. So we have to consider those scenarios. And then in the normal designs, we have, of course, the global analysis, and then the analysis of parts of structures, and then the member analysis. So in the global analysis, we are looking at the overall performance of our structures, and then how the compartments behave, and then how the members are behaving in structural fire. And then in this compartmental designs, of course, I know in Sri Lanka, there are specified areas or volumes for these compartments depending on the type of the building, and also the effect of openings to be considered, and also the height of smoke, because smoke is one of the causes for most of the deaths due to fire. So this smoke height maintenance is very important. And also then when we go to the local member related areas, so we have to verify the material strengths, the strength of members, and also the protection of those members in our analysis, and also the numerical simulation. So what I am showing you is some of the work we have done by our team at Preparedness related to the cladding related studies, like the fire, the glass facade fire, and then various other sustainable materials. So we have done some work, and also because the simulations are possible now. So I think that's where we want to direct our nation, because we are talking about smart development. So rather than wasting a lot of time on real testing, if you have validated numerical models, so those are very easy and convenient tools for the predictions for the designs. And finally, this is my final slide about the regulations. I think, as I said, we have the Construction Development Industry Development Authority, the CEDA Act number 33 of 2014, which is the governing regulation on fire. And also now in that document, there are two main things to look at. One is, of course, the fire regulations given in this CEDA TEV 14 document. Those are the mandatory requirements, such as the fire escape, structural fire related detection, alarm systems, and those minimum requirements, the mandatory, and then the specifications. So when you have requirements, the specifications also should be given. Those are now this is one of the US guidelines that is referred by CEDA that we usually use in our fire designs. So I think with that I will finish my session at this point. So hoping to have questions and answers, and back to the moderator, Dr. Herath.
Right. Thank you, Professor Bandar. I think that was a very insightful discussion, and I think you looked at mainly 4 different aspects on the natural disasters and how the construction and building sector contributes from various angles to this climate change, and also how the global stage, or how the other developed nations and also the developing countries look at this, the policy level decisions on rules and regulations. And lastly, you touched upon the design approaches, including all these Euro codes and the national annexes, and give some idea on where we are as of the global trends. Now, yeah, thank you, Professor Bandar. And I would like to remind all the participants, you can send the questions via the chat. So I will be collecting all the questions, and I will be raising them at the end of today's both sessions after Dr. Veerasinghe's session. Right. So with that small remark, we will move on to our second speaker of the day. And Dr. Pasindu will be the second speaker for the day. And Dr. Pasindu Veerasinghe obtained his bachelor's degree in civil engineering from the University of Moratuwa in the year 2015. And he was the recipient of the award for the most outstanding graduate of the Faculty of Engineering and the gold medal in civil engineering at the convocation ceremony. After graduation, Dr. Pasindu completed an MSc degree by research under the supervision of Professor Anunanayakara, and the research was on plastic shrinkage cracking of fresh concrete. In 2016, he received the Melbourne International Research Scholarship to pursue a PhD under supervision of Professor Priyan Mendis at the University of Melbourne, Australia. His research was focused on the fire performance of concrete flat slabs, and he was also a student at the Center for Advanced Manufacturing of Prefabricated Housing, and also he got involved in several industry-funded research projects related to modular constructions. And he's a team member of the Innovative Facade and Fire Engineering Group, which is a collaboration of several key Australian universities which conduct research related to fire engineering. After completion of his PhD in the year 2020, he joined the Department of Civil Engineering at University of Moratuwa and currently working as a senior lecturer attached to the Building and Structural Engineering Research Group. His research areas are structural fire engineering, fire safety, performance-based design, concrete technology, and modular construction. He is currently the president of the Society of Fire Protection Engineers, Sri Lankan chapter. Over to you, Dr. Veerasinghe.
Thank you very much, Dr. Somudu, for that kind introduction. I hope that I'm audible, and
Yes, Dr. Veerasinghe.
and then moving on how disasters affect the fire or the fire safety of structures, and some of the state-of-the-art work that was done in order to identify these safety issues and how to rectify these in terms of structural engineering. And so my duty here is to continue from that point onwards, and so I will more focus on the fire safety side of this. And so the content of my presentation is based on these 3 main topics. First, the multi-hazard reality. I mean, what happens when a fire strikes with a disaster concurrently. So, I mean, disasters as fire triggers and the second wave effect of fire. And also when the fire is a secondary event, what is the compounding effect of that and how the primary damage or due to seismic or the flooding effect compromises the fire safety. That is the first part of my topic. Then I will move on to the material science and the structural integrity, because now we are talking about these climate smart structures, futuristic material. So I want to shed some light on how these materials behaving in fire, focusing on three main materials: uh, mass timber, CLT, high strength concrete, and modular steel buildings, and some characteristics of those materials. And finally, uh, I mean, as engineers, how we can tackle this question of fire happening with a disaster, and what are the measures, passive versus active protection in design scenarios. And finally, as Professor Bandar also mentioned, what are the regulatory gaps that we have in our country and where we should move if we want to address these issues in a sustainable manner. Talking about moving from prescriptive code-based design approach to performance-based fire design. So before I go into the um, details, so now I hope you, I mean, maybe if you are born in that time, you may remember this disaster, 2011 World Trade Center collapse. And so if you are, I mean, you may probably would have heard of that. According to you, or according to your knowledge, what could be the reason for the catastrophic failure of these twin towers, right? I just want to get your idea, so you can just scan the QR code, or you can go to this slido.com and type this number there, 6471855, and join this poll just to break the ice and have some discussion among ourselves. What could be the probable cause of failure for this World Trade Center collapse in 2011? Right, so we have a couple of answers ranging from columns, structure, jet loads, bombs, fuel, temperature, and excessive energy and imbalance. Yes, I mean, the word that I was looking for is still not there. Maybe we'll move on to this next slide. So thank you for your enthusiasm. Yes, I can see one other participant is typing. We'll give 1 minute if anybody else is willing to join. Hitting the center of gravity, geopolitics, yes, in a way it is true. I mean, was a terrorist attack after all. So steel columns are not fire protected enough. Yeah, I mean, we are getting there, I think. Actually, the columns were fire protected, but due to the, okay, we'll discuss the real reasons now. Now, I mean, this was a tube in tube structure. So we have an inner tube and outer tube, which are closely spaced columns act as an outer tube and the inner tube. So the rigidity of the structure was given by these two tubes, and they were connected using these lightweight floor trusses. Now, when the plane impacted on the tower, there was damage for this outer perimeter. So the outer, the tube was damaged. But actually, this was designed for such an impact load, right? So actually in the design, it was considered if an accidental damage happened to the outer tube, whether the inner tube will resist the lateral loads and whether it will hold the structure without any catastrophic failure. But the next thing that happened triggered the progressive collapse. So there were a lot of fuel in this aircraft, and then due to the blast impact, these fuel got ignited, and then there was fire. And due to the impact of the blast, the protective layer that was protecting the steel members from fire got damaged, and now the steel is directly exposed to these fires, which will estimated about 1500 Fahrenheit. And then one by one these steel members start to yield and fail. So then the other steel members were loaded extensively, and then the upper part fell, and due to the gravitational momentum, it resulted in a progressive collapse. So this was the final output of the investigation, and you can see now the culprit is the secondary fire that has happened after the blast impact, right? So this is a good example where fire has happened as a secondary event, so after a disaster. So this is not a natural disaster, it's a man-made disaster. And then if you think about the earthquake situation where ground shakes, and it could result in failures in gas pipelines or power failures or failures in power lines, and these would cause a secondary fire or gas fire or electrical fire. And due to the disaster situation, one thing is it is difficult to control. The firefighters will have difficulty accessing, and also the scale of the disaster is significant if it is like an earthquake event. So it is another case where a disaster will trigger a fire event. And if I take another example, the wildfires. So wildfires, if they are not controlled, they can reach the urban environment. And in wildfires, there are certain things generated called embers. Embers are these flying heated particles. So due to the wind, they will get carried away, and when these flying embers uh, hit on or touch on a combustible surface, it will create, or it will ignite that surface as well, which will cause a fire a certain distance away from this wildfire. So this is called the wildfire interaction with urban interfaces. So that is again, the disaster was a natural disaster, wildfire, but it is turning into a catastrophic fire event, secondary disaster that could affect our own livelihoods. So this is a very good example of such an event, the Kobe earthquake that was happened in 1995. And after the earthquake, it was reported that approximately about 300 fires were reported. And you can see from this image the scale of the devastation that has happened there. So the probability why it happens is it's like that is it could ignite due to toppled furniture or movement of hot equipment or electrical short circuits. If it causes the ignition, then it can spread. So therefore, in disasters, so fire is often the second wave that causes significant structural damage. And in case of an event like Ditwa, what could happen in the context of like in Sri Lankan context? Now, if a structure is subjected to flood or wind damage, so the structural integrity is compromised. So it will have openings, it will have cracks, and no longer a fire can be contained in a certain place. So we call it in fire engineering term the compartmentation of fire. Containing the fire within an enclosed environment. So that is not possible if a damage like this has happened. So then as a secondary event, if a fire occurs or fire ignites, that would be uncontrollable. It will quickly reach the flashover stage, and also, difficult for firefighters to access such scenarios. Right. So it's a multi-hazard degradation. So we call it as compounding stresses. So the stress that occurred due to the disaster is elevated due to the secondary effect of fire. So, due to the primary disaster, it could be a blast, impact, or a seismic or a flood event. The structure faced severe secondary thermal loads due to a secondary event, and that initial disaster often cracks the fire resisting compartment walls or strip away any sprayed fireproofing if it is a steel structure. Then the secondary fire will induce extreme thermal expansion or catenary forces on already damaged structural frame. And finally, this combination of mechanical damage and the material degradation, dramatically, it will increase the risk of progressive collapse of the structure. So before this is the background to my presentation. Before we move ahead with the other slides, I would like to give you a brief overview of some of the technical terms that we use in fire engineering. Now, to categorize a fire, we use a time temperature history, and this is the behavior of a natural fire curve. So it will have a ignition phase and a flashover stage and the ultimate stage, and then finally the cooling stage. So the ignition phase can take about, these are rough figures. During the ignition stage, the temperature will increase slowly, and then this scenario called flashover will happen. Flashover means suddenly all the combustible material that is in the vicinity of that particular compartment will catch fire. We call it as a flashover. So after the flashover, you can see that it grows rapidly. So before the flashover, we call it as a pre-flashover stage. These temperatures are just estimated values, figures. And after the flashover, the fire will grow rapidly and it will reach the fully developed stage after the flashover point. And then after the fully developed stage, maybe the fuel will run out or maybe the ventilation will cease. Probably the most common thing is the fuel running out, and then it will no longer burn, so the fire will decay gradually. So that is called the decaying phase or the cooling phase. So now this is the natural fire curve, but in our designs, we will represent that using something called a design fire curve. Or a design fire curve, we don't usually represent this ignition phase. We assume it as a fully developed fire, or post flashover behavior is represented by the design fire curve. And you can see another difference between the design fire curve and the real one. The design one does not have a cooling phase. It is a ever increasing fire, whereas the natural fire will decay after some time due to certain reasons that I mentioned before. Right. So during the pre-flashover stage, if you have extinguishers placed, active fire control measures like sprinklers, fire alarms, heat and smoke, or basically evacuation should happen presumably before the flashover stage. Right. And then right. So post flashover, now the only option that we have in controlling the fire in the post flashover stage is by compartmentation. That means enclosing the certain area and making sure that the fire is not escaping from that confined space. And the firefighting will happen within this region. If the active fire measures fail and the fire reaches the flashover stage, then it will go to the firefighting stage. And this is where our structural fire safety matters, because post flashover, if you can't control it with using the active fire, then the structure should withstand until the fire is controlled or until it reaches the decaying phase. So the passive fire protection that I'm going to discuss next is based on this post flashover behavior, and the fire investigation can happen after it has decayed or cooled down. So we have several standard time temperature curves which can represent the behavior of a fire. Typically what we use is the ISO standard fire curve, which look like this. And in certain cases, the fire will be severe than that. So such as car parks or where you have more fuel load. In such cases, we will use a fire curve called the hydrocarbon or some other fire curves which have a much severe, the increase in temperature is rapid at the early stage. And the severity of a fire will be identified by not by the maximum temperature the fire reaches, but by the area under the fire time temperature history. That means even if it is a the fire having a higher temperature, but if it cools down quickly, the severity is less compared to a fire which lasts for a long period time, even though the temperatures are lower. Right. And then we have something called parametric fire curves. All these fire curves that I have shown here are design fire curves. You can see, certain cases you have a cooling phase, but these do not depend on the certain characteristics. Simply, it's a standard prescribed time temperature history, irrespective of the characteristic of your structure. But in certain cases, we may have to look into the structure as well. Depending on, the fire is influenced by how much openings you have, what is the ventilation condition, what is the geometry of the space that you are having the fire, and how much of a fuel load is having there, and what is the material that is being burning. So if you take all that into account, we can generate something called a parametric fire curve. So it is having an increasing regime, flash show stage, post flash show, and then the decaying phase as well. And then the higher temperature and the duration, the decaying phase, everything will depend on those factors that I have mentioned. So if you are actually, I will later mention what is meant by performance-based design. So if you're actually going for a performance-based design approach, these parametric fire curves will be the ones to use. And the same thing that I have mentioned before, I will not spend too much time. The severity of the fire is actually described by the area under the time temperature history. Okay. And then finally, what we need is a certain fire resistance from our structural members. So the fire resistance level can be categorized into three main, can be measured by three criteria. First one is the structural adequacy, that is the ability to maintain the load bearing capacity for a duration of period when it is exposed to fire. That is called the structural adequacy criteria. Then the integrity, ability to act as a barrier that will resist the passage of flames and hot gases. So if the fire is burning here, this should act as a barrier for a certain time period where smoke and flames will not penetrate to the other side. And finally, the insulation, the ability to maintain the temperature of the unexposed surface for a certain period of time when the fire is happening on the other side of the element. So if you say, usually these fire resistance levels are given as a time period. And if you say 60, 60, 60, that means when it is exposed to, let's say, a standard fire, until 60 minutes, it will maintain its structural adequacy. Until 60 minutes, it can maintain the integrity criteria. Until 60 minutes, it will maintain the insulation criteria. So it is a 1 hour fire rated. It can be a fire rated wall or a fire rated door, or it can be a fire rated structural element or non-structural component. Right. Then, as fire safety engineers, our aim is to mitigate the impacts from the fire hazard. So first line of defense is, we have these fire safety provisions and fire codes, as Professor Bandar mentioned. Our one is ICTAD fire regulations, and they are developed to incorporate appropriate measures to mitigate the destructive impact of fire in our structures. And the mitigative measures can be in the form of preventing the ignition in the first place, and also if the ignition happens, then minimizing the fire spread after that. That could be one approach. The other approach is, if the ignition happens, we have to facilitate the safe evacuation of occupants before the structure fails. And thirdly, until this fire is controlled or contained, we have to make sure the structural integrity is maintained. Structure will not fail until the fire is controlled. So in order to, these requirements will vary from type of the building, occupancy level of the building, the materials being used, and also the building height and the compartment area. So we can't have one solution for all the structures. It will be a building specific or structure specific solution that we have to incorporate. Right, as regulation wise, CEDAW regulations is there, and if you look at the global arena, the International Building Code, the National Construction Code, or NFPA guidelines, these are some of the prominent fire codes that we are using. And minimizing the fire spread, we called as the compartmentation. That is like the basic concept in passive fire protection. But however, how much we try to minimize this harmful effect, it is not possible to prevent an event of fire because it's an accidental event, right? So in that case, so as designers, what we do is we place certain strategies to minimize the occurrence of this. And if a fire occurs, we are trying to minimize the consequence impact on our lives, property, and the environment. So that can be achieved by two means. One is through active fire protection systems, which are activated when a fire occurs. Examples are fire sprinklers, fire detection system, and so basically fire detection and fire alarms, things like that. Basically, they react to fire. That is why they are called active fire protection systems. Then the other side of this is the passive fire protection system. So these are not activated, these are just there inbuilt in the structure. So one passive fire protection measure is barrier walls or fire doors to control the spread of fire, basically to maintain the compartmentation. And in case of evacuation, the building or the structure should have safe travel paths for the movement of occupants as well as the firefighters to come into the building and fight the fire. And finally, until we all do all those things, the structure should not collapse. So we need a fire resistant structure. So these measures, they are designed to contain the fire if a fire occurs. So in case of a disaster, I will talk about it later as well. This active fire system, there's a chance of malfunctioning due to various reasons. So in that case, our last line of defense is these passive fire protection systems. So in terms of the differentiability, in terms of mechanism, they require some kind of triggering for the active fire systems, but passive fire protection, they relies on built-in properties. So inherently, they are there. Effectiveness, mainly active fire protection systems are effective in the early stage of the fire, free flash off as I shown you before, but passive fire protection, even in the fully developed stage, they are effective. The objective of active fire protection system is to extinguish and facilitate early evacuation, whereas passive fire protection, the purpose is to contain and ensure structural integrity or stability during a fire. So for the next 5 minutes, I will briefly talk about different material behaviors under fire, mainly talking about timber, high strength concrete, and modular steel frames, because now we are moving into this era of sustainable construction, and we have to look into these futuristic materials and how they behave in fire. So in terms of concrete, especially in high strength concrete, spalling is one of the critical issues. That means when it is subjected to fire, this exposed surface of concrete will dislodge, and what it does is it reduces the effective cross section of your concrete member, and also you can see the reinforcement is exposed to fire. So overall, that reduces the overall capacity of the member, and it increases the risk of failure. So why concrete spalls? Mainly because of the poor pressure development during fire. So in case of a fire, the moisture that is trapped inside the concrete, they try to move away from this heat, or they try to penetrate inside, but cannot go to, there are no free paths as such. They have to move through the pore structure of concrete. So somewhere then they will be stagnated and the pressure will be developed. So once this, when this pressure develops, what it does is it causes an expansion, or it try to expand from the inside, so causing tensile stresses. And once that exceeds the tensile capacity of the concrete, this part will lodge or detach from the original structure. So if you have a high moisture, rapid heating rate, slender members, or high concrete stresses, or low permeability, especially in high strength concrete, they are low permeable. All of these increase the risk of spalling in high strength concrete. So then what is the solution? One solution can be adding these small polypropylene fibers to the concrete. So what it does is at around 200 or 300 Celsius, these fibers melt, and then they create a path for the pore pressure to release. So if this pore pressure is released, that will not generate high tensile stresses. So that way we can reduce the risk of spalling by adding these fibers into a high strength concrete. And another material that is becoming more popular is the timber. Now, timber, although we think it as a combustible material, certain characteristics of timber are actually beneficial in fire. So, timber, begin to pyrolyze at about 200 Celsius, and they turn into char at 300 Celsius. This charred timber, or this charred timber, is this black colored part. That is, of course, beneficial because it acts as an insulation layer, and it protects the inner timber from further charring. So this then the load carrying capacity of a timber member that is subjected to fire will be depending on this protected layer. We call it as a residual cross section. The charred timber, they can't be used to carry any loads. So therefore, the design or the fire resistance of timber members will depend on mainly this rate of charring, right? When it is subjected to a fire, how fast this charring, how fast it will char, and how fast it will reduce this usable residual cross section. If it is charring too much or too fast, that is not preferred. If it's charring slowly, that type of timber can withstand for a long duration of time. Now, this cross-laminated timber is becoming, now we have some multi-story buildings as well from the CLT. It's becoming popular not in Sri Lanka but in other parts of the world, Europe and Norwegian countries. CLT buildings are now popular, and they have a higher superior structural performance and can be used as even columns in tall buildings. But the fire characteristics is the one to be questioned, because now, unlike normal timber, once this is charred, so because it is constructed using several layers, that charred layer will fall off. Once that fall off, the new new timber is exposed, and that will be subjected to fire. So, then the charring rate will increase overall in cross-laminated timber. So, risk of delamination and exposing new layer into fire, these are some of the issues that need to be addressed in CLT members. And finally, I will touch on this modular construction. So modular construction is this off-site fabrication of buildings. It's like just building blocks putting together to make a final structure. And now this was a new topic for Sri Lanka for so many years, but now actually the contractors are using this modular technique even in for tall buildings, which is a good thing. And especially in this disaster situation, this modular construction can be the game changer because you don't have enough time to go and construct an in situ buildings on this site. So in that case, these modular constructions can become handy. So I mean, since they are constructed off-site, they will provide about 20% to 50% time saving, 20% cost saving, less wastage. So what it does is, I mean, the steel members put together and then put it as a volumetric assembly along with MEP services and finishers, and then transported to a particular site and then assembled to build the final structure. So in this modular construction, the concern is these cavity spaces that can generate or that is inherently there between these modules. So if a fire can penetrate into these cavities, it can travel vertically as well as horizontally throughout the building, which is not the case in normal buildings. We don't have such cavities. So in terms of modular buildings, the fire risk in this cavity fire risk is significant. I mean, I've not spent too much time. These are the recent disasters that has happened in this module. You can see here the fire spreading through the cavities. So, I mean, we have done some research on this cavity and how the cavity fire will affect the structural members, since this is not a really, I mean, don't know to go into too much technicalities, but if you have any questions on this, I'm happy to answer. But the basic problem is compartmentation is difficult here because of these cavities. So, I mean, we have to either seal this cavity or, I mean, using fire stops prevent the spread of fire within these cavities. And so some kind of measure should be taken. Right. Then the I mean, I'm reaching the final stages of my presentation. So in terms of a disaster, how disaster and fire protection system responds to it. So in terms of disasters, mostly these active fire systems may fail. So it can be due to a broken pipe due to earthquake situation. In terms of this flooding, these submerged pumps. So it actually happened in a lot of places in Colombo as well. According to these fire brigade officials, the fire pumps were located at the ground level, got flooded during this disaster, and luckily we didn't have catastrophic fire events. But if a fire event occurs, then the pump would not be working in such a situation, and due to the power outage, these alarms and systems may not work, and due to the structural failure, the evacuation paths may get obstructed. So in terms of passive fire failure, the last defense that we will have is so in terms of active fire failure, the last line of defense that we will have is the passive fire protection system. So, I mean, I will finish my talk moving on to that area of passive fire protection and little bit touching about this performance-based design. That will be the final part. So in fire design, normally what we have is we will have certain performance requirements based on the type of the structure. Then to meet that, either we can use a deem to satisfy the code-based solution, where it is a prescriptive one, or we can go for a performance solution. I will explain the terms later. So deem to satisfy solution is, for example, we will categorize the building according to different building classes, and based on the building class, we will see what is the fire resistant level or the fire class of fire construction required. So based on that, we will have a certain fire rating, a number. Then we will design our members to meet that specific fire requirement using a prescriptive guideline. Let's say the minimum slab thickness to meet a 2-hour fire requirement would be 200, a flat slab and a cover of 35 millimeters. But I mean, that will not work most cases. The reason is now prescriptive based design solution is the acceptable solution, and it is using standard fire curves and standard data. But in the actual situation, the fire will have a decaying phase and a fully developed stage, or maybe the fire will not reach the flashover stage at all. So in that case, the fire will, I mean, the behavior of the fire will depend on the compartment size, the ventilation conditions, or the fuel load. So if you incorporate everything and develop the natural fire curve, either by a parametric model or by fire simulations, if you apply that natural fire curve to a structure and see what is the behavior, that is called the performance-based design. So the performance-based design can be done either by using fire tests, I mean, to get the necessary data for our simulation or the modeling, or we can do fire modeling or a couple, I mean, the coupling of fire test with fire simulation data. So, I mean, basically, this is the approach that is more suitable for an event or a secondary fire that could happen in a disaster situation, because in a disaster, we will not have a normal structure, we have a damaged structure. When the structure is damaged, what could be the secondary effect of fire? So the standard or the prescriptive guidelines will not account for such events. In that case, only approach is to go for a performance-based design. So, I mean, in conclusion, if I summarize what I have been discussing up to now, so fire is an inherent disaster risk, so we cannot prevent all fires. It will be anyway there. And these natural disasters actually can trigger a secondary fire event. We need some resilience in our buildings or redundancies, because active fire systems may fail during a fire. So therefore, our last line of defense is the passive fire protection system. And the materials matter. So as we move towards this sustainable, climate smart material, mass timber, high strength concrete, we must explicitly design for these unique behaviors such as charring or spalling risk. And finally, the approach should be not to go for the prescriptive rule based design, but to go for the performance based engineering approach that will account for real world fire curves and also these disaster weakened states. So with that message, I would like to finish my presentation and would be more than happy to answer any questions during the Q&A time. So hope you have got some idea what is this.
Thank you, Dr. Veer Singh, for the insightful presentation. I think there's a lot of information from various aspects of engineering, but that all led to the fire and the respective safety aspects that we have to look at in terms of the analysis and design aspects. Now, once again, I would like to remind the participants, now you can send all the questions via the chat. So I'll be picking the questions and then I'll be directing them towards the two speakers. And may I invite Professor Bandara and Dr. Veer Singh to join the session. Yeah. Okay, so the first question I will direct it towards Professor Bandara. Professor Bandara, so in terms of this climate resilience and the futuristic designs that you mentioned in your presentation, what is the current trends in the global arena and also how it is merged into the context of Sri Lanka?
Yeah, thank you. Yeah, actually, the futuristic design concepts, I mean, in global arena, yes, there is a trend to go for those futuristic designs. I think that is how we are going to this concepts of green cities, green buildings, and smart buildings, and things like that. So because there what is expected is once again to use the smart materials, the technology, the sustainable materials, and the reduction of energy and all those concepts in buildings to have self-sustained structures and buildings. So I think that is the direction the world is on now. In Sri Lanka also, I think now we have various organizations in the country looking at that direction. Even the UDA now they are in that direction about the sustainability and those sustainable designs in their approval process. Also, we have the Green Building Council and like organizations to this direction. But I think we should go further with the smart materials, smart technology, the use of AI, the ML, because even in those green concepts, those are not yet adequately integrated to the designs. So I think that should be the direction that we should be focusing on, because when the green concept came, it was around 2005, 2006. At that time, these AI, ML, those technology, those were not there. So I think therefore those also should be changed and integrate the AI, ML, and all these new concepts to those existing the concepts.
Right. Thank you, Professor Bandar. And the second question I will direct with Dr. Veerasinghe. In disaster scenarios where fire allows structural damage from various sources, how can modern computational tools or machine learning can improve the risk of early risk assessment and the design decisions? Dr. Pascal, what is your opinion on that? The use of computational modeling tools and the use of machine learning?
Yeah. So I mean, now things like digital twin models of buildings, and also now predicting the behavior using machine learning, those are the new trends that are being tested in this area. So digital twins actually seems to be a successful, I mean, or some sort of working model to simulate the scenarios and to predict what is going to happen next and to act swiftly accordingly. But I mean, up to now, the machine learning methods to a certain extent to determine the material characteristics, machine learning is applied, but to model the overall behavior of fire, it is difficult, because even without machine learning, with computational fluid dynamics, it is somewhat difficult to capture certain localized behaviors. So maybe, I mean, in the future, when these things get developed and when more data comes, data becomes available, maybe we can rely on machine learning. But up to now, it is difficult to rely solely because we don't have so many experimental data that can be modeled and tested using machine learning.
Right. Okay. I think he cleared the doubts on that. And Professor Bandar, the next question is on the material scarcity. So there's a question whether there'll be a real problem in the future, because now people are looking at some new innovative materials on top of these reduction, reuse, and recycle options. There are certain things in the research stage, and also there are certain things already sort of in the commercial stage. So maybe your opinion on that would be really helpful.
Yeah, thank you again. Yes, now, yeah, that is correct. Because, of course, there is a material scarcity, and one of the solutions is the use of, I mean, recycling, reusing the existing materials, and also then going to more advanced or more efficient material, as Dr. Pasindu also mentioned, like now even concrete with steel or the carbon fibers, we can go for very high strengths. I mean, reducing the quantities, but increasing the strength. I think so. Therefore, um, with the innovations, with these new introduction of new materials, yeah. But the problem is, I mean, that will reduce the problem up to some extent. Not 100%, right? Because still we have to use material, right? I mean, to develop those, even those new materials. So it's not a pure 100% good solution, but there is no option. So because we have to expand the cities, we have to develop the world for the, I mean, for the people. So the only way we have is to minimize the resource utilization. In that respect, yes. So those are the concepts, I mean, already ongoing, the findings or the research work and the materials that we are kind of developing. But it's not 100% a solution, but that is what we can do actually.
Yeah, I think that's a good point that he raised. I think maybe the scarcity, maybe the rate of scarcity would slightly go down. However, it will be anyway going towards the loss of raw materials for all these. Right? I think that's.
Yeah.
And in your opinion, Professor Bandar, now what are the steps taken by various institutions in the direction of futuristic designs in the context of Sri Lanka? Maybe with some examples we can think of.
I think for the moment, what we can see in the futuristic design, direction is these mainly. I'm talking about these. I mean, in the application, what we can see in the country is so-called the green buildings. But as I said, still I think we are not to that smart building concept. So now still we think the green buildings are, buildings with some green features and maybe some solar panels, some rainwater harvesting systems and things like that. But it should be more than that. I mean, the building should be kind of more smarter that we have to look into. I mean, in the futuristic designs. I don't think we are yet there, but we are in that direction. As I said, through the green building concepts and all that, we have number of green buildings already, even accredited by even LEEDs certification. So I think we are in that direction, but not to that, the smart buildings yet.
Right. So thank you, Professor Bandara, on that as well. And once again, I would like to remind the audience, you can send your questions in the chat. We have about 10 minutes more on the questions. And next question is to Dr. Veerasinghe. The question reads as, what will be the probability of fire occurrence after natural disaster in Sri Lanka? And the responder thinks that it will be very low compared to a structural collapse. And also he or she is adding another aspect. Was there any data about secondary fires after Ditwa, the recent events?
So actually to quantify, I think there are no data as such to quantify, not even after disaster, even the fire events that we have. I mean, that happens in different regions, and you know that, I mean, different fire brigades are involved in controlling these ones. So we don't have a unified data system as such to quantify or to say anything about the probability of occurrence. But however, luckily, I mean, as I mentioned, no major events of fire has occurred after a disaster. Now, especially after disaster like Ditwa, I mean, because the conditions are wet and flooded, maybe the probability is low. But in case of like now earthquakes, we I mean, we felt some tremors recently as well. So now we never know when is the next big earthquake. So in such an event, actually, an urban area like Colombo may be susceptible to these secondary fire effects. And in Ditwa, I mean, not in these remote areas, but the Colombo region also got flooded. And even, I mean, lot of these pump houses uh, that were controlling the sprinkler systems or emergency fire controlling measures were flooded. And even after the flood uh, went away, for until few weeks, I mean, they were not functioning because you have to fix them, you have to bring in new pipes, and I mean, control system, you have to maybe fix it. Then during that time, if a fire happens, it can be a devastating one, because I mean, now the active fire measures that were put in earlier are not functioning anymore. So that is uh, the what do you call, the observation from the fire brigades like the Colombo Fire Brigade, especially in this Ditwa situation. And also, I mean, we don't have separate, or we have a disaster management system, but during that particular disaster, even the fire brigade were asked to help in certain non-fire related events, such as maybe cutting down trees or rescuing people from stranded areas, because they have the equipment. So I mean, in a way, actually, we are, I mean, diverting our effort to another situation. And if a fire occurs in that scenario, I mean, they wouldn't have enough fire trucks to respond. These are like one-off events, but I mean, we can learn from these things and plan accordingly. If something in this scale and this nature happens again, what could be our coordinated response?
Right. And the next question, I think we both, Professor Mandar and Dr. Veerasan, can add from various along various directions. The question is, are existing rules and regulations in Sri Lanka adequate for the design and construction of climate resilient structures? And also, are the same rules and regulations adequate for structural fire aspects? What is your maybe Dr. Pasdu can add on the fire aspects, whether the current or the existing rules and regulations are adequate. Are we in par with the global trends, or where are we?
Yeah,
Please go ahead. Okay. Yeah, I think now the existing rules and regulations related to the normal building designs for the futuristic building designs, I think are not adequate, because now, for example, now we are talking about at least the sustainability. The building should be sustainable. We have to at least have some, at least the water to be recycled, or kind of at least to use rainwater, maybe at least for toilet flushing. Even those concepts are there. Those are not mandatory requirements. Now, to have a solar panel on the roof is not a mandatory requirement yet in the country. So therefore, I think we are not yet there with the rules and regulations. But there are countries like Australia, for example, there are some mandatory requirements like having this percentage of renewable energy, this percentage of recycled water. I think we are not yet to that level. But what I'm saying is there's a trend. So there are groups working on those areas. There is a trend. Even now, the private sector, even the universities, I think I have seen trying to kind of use maybe 10% or 20%, 30% of energy using solar. So those trends are there. Those are good things, but not mandatory. So that is the issue. So I think we have to change maybe little by little the rules and regulations so that those important sustainability aspects are mandatory in our construction, in our designs.
Mm. And Dr. Veerasinghe, another question on the national annex and the evolution, the initiation evolution of fire. Does it depend on the location it happens, whether it is in a different country versus Sri Lanka? And what is the state of like a national annex development for fire design in the Sri Lankan context? Is there a real need? What is your opinion on that?
I mean, in the Sri Lankan context, as Professor Bandar also pointed out, we have the ICTAD fire regulations. Mainly, it's a prescriptive base code. I mean, it does not describe about these performance-based requirements, such as if the fire happens at different location, or the fire intensity changes, what happens, or if the amount of combustible material changes, what is going to happen. I mean, such flexibility is not there actually. Therefore, I mean, that is why there's a great need as a country for us to go towards performance-based fire regulations, and the world is moving towards that direction, and sooner or later we will have to catch up with the rest of the world as well. And as far as I know, there are certain plans to develop a national building code for Sri Lanka as well, and in that a certain chapter will come as a fire, just like the national construction code in Australia. And hopefully, I mean, that will be based on performance-based design, and it will give some opportunity for these fire testing simulations and come up with a tailor-made solution for our own structures, rather than relying on a prescriptive all fit for one solution. So yeah.
And yeah, to the audience, we have about 3 minutes more. If you have any questions, you can send it in the chat. And maybe on the research aspects now, on this climate resilient designs, maybe Professor Bandar, would you give maybe a couple of examples, like what are the active research projects that are ongoing, especially at Peradeniya, where you are a professor, and also in the Sri Lankan context, what sort of research projects are being conducted?
Yeah, I think, I mean, at the research level, I think there are a lot of research work going on, not only actually in Peradeniya, everywhere, in almost all the higher educational institutions like universities. Now, in Peradeniya, of course, I know in Moratu also, in the materials as a department, we are, of course, working in some projects together on concrete printing, 3D printing of concrete, for example, and then the use of recycled plastic in concrete, and in some other materials, in the construction material. Of course, there are a lot of work by a lot of eminent professors from like year 2000 around the use of recycled, of course, the construction demolition waste in concrete products and all that. So I think at the research level, that type of research is going on. And also, there are work on these materials required for the energy, like the solar panel production and all that. So those research also is going on. And also, I think in the AI related work is also going on by various groups together with, for example, especially the health monitoring of structures using machine learning and AI. And also the kind of real-time monitoring of structural health using the various machine learning algorithms and image processing. So I think a lot of work is going on throughout the country by the researchers. Only thing is, one thing is, of course, there are supporting agencies also, like the National Science Foundation is funding for most of those research, I know. And only thing is now they are at the research level, and usually, to bring them to the products level, I think is the challenge. I think in Sri Lanka, most of the researchers are, kind of, now as academics, I think we have, we are not so good in doing business, to putting those research to products. So I think that is where private sector should join a hand with the researchers, so they can do the second part of it, like putting those to market. So then those will be kind of used by people. So that is just the comment that I can give about this ongoing work. Of course, lot to do, but it's going on.
Thank you, Professor Banda. I think I'm sure there are students also have joined to this session. So every academic in any university, they have a Google Scholar profile. So if you are more interested in the current or the latest work that they do, you can go and visit their scholar profiles and then get more updates on their research profiles. And maybe Dr. Veer Singh, you can add a bit more on the research on the fire that you and the other researchers in Sri Lanka have been working on.
Yeah, I mean, we have developed some fire testing equipment at University of Moratuwa as well, and recently there was a state-of-the-art fire testing lab open in University of Sri Jayawardhanapura, so they have very good equipment there. And I know that other universities like Peradeniya and other engineering and technical faculties also trying to do this fire testing and also fire simulation. So I mean, glad to see that it is becoming a hot topic or interesting subject area. And I mean, as the way forward, I think we have to promote these researchers or our findings for the decision makers and push them towards improving our guidelines or fire codes, and basically finding something tailor-made for a Sri Lankan context, because our material characteristics, our climate, our fuel loads, our ventilation may be different from other places. So we have to see what are the fire characteristics and how our own material is responding to these fires. So we have a golden opportunity now. So I invite all the interested people who may have listened to this, students or PG students, I mean, to pursue interest in this fire or the smart material, climate resilient, sustainable engineering area.
Thank you, Dr. Veer Singh. I think that's a very good aspect. And also, I would like to invite the people representing the industry as well as the academics. We can always collaborate with all these cutting edge tools and equipment that we have in the Sri Lankan university system. Yeah, and with that, I think we have run past 3 minutes after 9. And so now I don't have comments from the audience. So then I think we had a very fruitful session for 2 hours, and I would like to thank Professor Bandar and Dr. Veer Singh on spending their valuable time and also answering the questions raised by the audience. And to make the concluding remarks, I would hand over the session back to Ms. Umayangana. Over to you, ma'am.
Thank you very much, Dr. Sumudhi Herat, for accommodating that meaningful conversation. And of course, thank you, Professor Bandar and Dr. Singh, for the insights that you shared. And I believe that the audience got an understanding as to how structural engineering helps in disasters, and also how safety planning can ensure that all these buildings and structures are staying intact. So thank you very much for spending time and joining with us in sharing your insights on that. So with that, we have come for the latter part of the session, and I would once again ask all the attendees to fill the feedback form that is being shared in the Q&A session here. And thank you very much for your interest, and we hope to see you all in the next webinar that is going to happen next week. And please stay connected with our social media profiles to get updates on the next webinars. So thank you very much. And once again, thank you, Dr. Herat,